Hello, and welcome to our sugar caking experiment presentation. Have you ever checked on an already open box of brown sugar, only to find that it was rock solid? Or have you ever stopped to think about the difference between a sugar cube and regular granulated sugar? If you're not sure of the cause behind sugar getting hard, here's a hint. That's right. Water, or more specifically moisture, has a big impact at a small scale. When a powder absorbs moisture from the air and forms lumps, it is described as caking. Let's get into the mechanism of sugar caking. Moisture content and water activity are big players in the mechanism of sugar caking. Moisture content is the quantity of water present in a material. In the case of food, that would entail fruits and veggies, meats, breads, and of course, sugar. Water activity, on the other hand, is specifically the amount of water present in a material which is free. More specifically, water activity represents the water which is not bound to the binding site present within the food material. A high water activity food such as strawberry has a lot of unbound water, which is available to support the growth of bacteria, yeasts, and mold. Sugar, a relatively dry product, has a very low moisture content and subsequently a low water activity. This means that there is an extremely low amount of unbound water. However, when water is present, the monosaccharides in sugar will undergo hydrogen bonding and a liquid bridge will be formed between granules. If the moisture is taken out, the bridge between the granules will still remain. When a significant amount of sugar granules form these bridges with each other, it is then that caking is visible. You may be wondering, how exactly does water just move in and out of sugar? It all has to do with relative humidity. Imagine the weather in a desert. Pretty dry, right? Now, imagine what the weather feels like right after a heavy downpour. It's like you can practically feel the water in the air. In this example, the first scenario has a lower relative humidity than the second, because it is a drier environment with less water vapor present in the air. Now let's apply this concept to sugar. Less water vapor also means less water vapor pressure, which is the driving force for water to move in and out of our sugar. Sugar is usually stored in cool, dry conditions during the manufacturing and distribution process. This means it is exposed to an RH, or relative humidity, of about 40 to 60% at around 25 degrees Celsius. When purchased, it may relocate to a very different environment, one that may be more or less humid. When this is the case, the relative humidity of the sugar's environment changes, meaning that the sugar is no longer in equilibrium with that environment. This is where vapor pressure and driving force come into play. The driving force of the vapor pressure that is present is what drives the moisture into the sugar. Depending on the difference in vapor pressure between different atmospheres, the driving force will either be small or very great. We've done a lot of explaining. Now let's get into our experimental design. The materials used were various salt solutions, plastic cups filled with either brown or white sugar, plastic film, an airtight container, a humidity sensor, and a small scale. Samples of sugar were measured out in the small plastic cups. Some of these cups were covered with a plastic film to emulate the packaging that store-bought sugar usually comes in. We will set up sugar samples in containers of varying relative humidity. These well-sealed containers are filled with saturated salt solutions and over time will create environments of equilibrium relative humidity. If a container filled with water creates an environment which is at 100% relative humidity, adding salt will hinder water from escaping into the air, resulting in a lower relative humidity. Adding enough salt until it can no longer be dissolved in water gets you a saturated salt solution, which in theory should have constant relative humidity in a closed system. For our experiment, we used 10 different salts whose saturated solutions can create 10 different humid environments. We also tested sugar in a water environment of 100% relative humidity, an open room temperature environment, and the oven. Putting sugar in the oven was done to find the weight of water and solid particles that comprise the sugar as a whole, as brown sugar does have a considerable amount of water, and white sugar contains a very small amount of water as well. To hold the sugar samples, Small plastic containers were filled with sugar and then set in the solutions on a raised platform. The sugar samples were kept in these environments for 2.5 weeks and were weighed for weight changes every other day. At the end of 2.5 weeks, the final weights were taken down, as well as observational data to grasp how the structure of the sugar had changed over time. Before we look at our results, let's go over the variables of our experiment. First, we have our independent variables, or the aspects of our experiment that we can control. For our first independent variable, we have our sugar samples. Here is an example of what our setup looks like. We have 3 samples of white sugar and 3 samples of brown sugar. In this example, the sugar is placed in a saturated salt solution made with NaCl. But there are also 12 other environments that are being tested, which brings us to our second independent variable, which would be the level of relative humidity. Here are all of our different environments besides NaCl, along with their respective relative humidities. Assuming the environment has reached an equilibrium state in the airtight container, the relative humidity should be constant. Now let's look at our dependent variables. As the name suggests, there are aspects or outcomes that depend on what is controlled in the experiment. Our first dependent variable is the change of the sugar's weight, and our second is the onset of sugar caking, or generally when the sugar begins to deviate from its original state. The different conditions that have been set based on our unchanging independent variables will cause the outcome of our dependent variables to differ. It is in those differences where we will be able to find patterns and make conclusions. In theory, the sugar sample should have reached equilibrium with its environment. In other words, it should have gained or lost the full amount of moisture possible based on the environment's equilibrium relative humidity. If this is the case, it means that a graph of moisture content over water activity can be made. This is possible because the water activity of the sugar at equilibrium should be the same as the water activity of the salt solution it's sitting in. The salt solution's water activity can be represented by this simple equation. Water activity, or AW, equals equilibrium relative humidity, or ERH, divided by 100. The graph that is created is known as a moisture sorption isotherm. A moisture sorption isotherm displays the relationship between the moisture content and the water activity of a product. The main use is to predict and extend the shelf life to ensure that the selected product is ready and within customer acceptance by the time it hits the shelves. Now, with the explanation out of the way, let's see what our results look like for our different samples. This is the moisture sorption isotherm that has been formed from white sugar being in different humidity environments. The label for most of the environments are shown, and we can see that until a certain point the moisture content stays relatively low, then shoots up. This is a result of the moisture content threshold being reached, which then allows water to come in at a rapid rate. The liquid bridges have formed in large amounts, eventually causing the sugar to liquefy. Next, we look at the brown sugar moisture sorption isotherm. As one can already expect, this isotherm peaks much earlier than the previous isotherm. Why is this? Well, to put it simply, it is because of the already existing higher amount of water from the added molasses that makes brown sugar, well, brown sugar. Due to this added molasses, the existing liquid bridges in brown sugar allow it to gain moisture a lot faster. This is the reason why brown sugar cakes more often than white sugar. In lower relative humidity, the brown sugar is one hard mass, as the high amount of hydrogen bonds have left behind bridges between the granules. Although these graphs may not be perfect because of possible errors that could have occurred throughout the data collection process, this graph still shows how much of an impact initial moisture content has on the gain of moisture in different relative humidities. Along with having brown and white sugar, we also have covered and uncovered sugar. As mentioned at the start of this video, the point of having this covered sugar was to roughly emulate the packaging conditions that sugar is typically in. The difference that packaging has is visible in the lowest relative humidity environment that we tested, that being magnesium chloride with an RH of 33 to 34%. You can see that the film is able to slow down the diffusion of water between the system and the sugar, even at such a low RH where not much moisture is present. Again, since magnesium chloride has a very low relative humidity, this causes the moisture inside the sugar to desorb so that an equilibrium can be reached between the sugar and the environment. In the next instance, we will look at sodium chloride, which has an RH of around 75%. This RH is higher than the average room RH, which is around 40 to 60%. When looking at all the different samples, Here we see the complete opposite of what had happened in the magnesium chloride set. Since this humidity is high, moisture is going into the sample, which again forces the sugar to reach equilibrium, but this time by gaining moisture. We see the caking occur and clumping of both sugars in comparison to the film sugars. Lastly, we look at the potassium sulfite group, which has an RH of around 97%. This is the highest RH environment that we tested outside of water. This means that it will have an even greater effect on the sugar compared to the sodium chloride solution, which is exactly what we see. The sugars in the uncovered cups have been liquefied due to the sheer amount of moisture coming in. The product has gone from a solid state to a liquid state, so it would take a considerable amount of energy to reverse the phase change. More importantly, we see that the film packaging has prevented the sugar from liquefying in this extremely humid environment. This further supports the positive relationship between proper packaging and shelf life, as the film sugar has not gone into a completely liquefied state like its uncovered counterpart. While sugar caking in itself is pretty unique and inapplicable to other foods, there are many different parts of sugar caking that can be applied in other circumstances. Texture and mouthfeel are very much seen to change over the course of sugar caking. We see this same change in products like potato chips or any food that has a crispy texture that is sustained inside a plastic bag. This bag prevents moisture from entering and altering the food inside. However, when removed from said bag, moisture immediately starts to enter into the potato chip, due to the high relative humidity in the air in comparison to the moisture content within the chip. The resulting moisture makes the chip stale and no longer crunchy. This all depends on the percentage of relative humidity within the environment. Another aspect of sugar caking is the use of a moisture sorption isotherm. We see that the use here is to identify when the possible onset of caking occurs and where the region of interest lies. Similarly, we can use this same moisture sorption isotherm to identify the time it takes as well as the threshold before a product molds, becomes soggy, gets stale, rancid, etc. Overall, the moisture sorption isotherm gives us an idea of just how long until a product is completely out of the customer acceptance range. This allows one to both predict and extend shelf life by manipulating certain regions of the moisture sorption isotherm to slow them down or speed them up to obtain a certain state of a product. A moisture sorption isotherm is one of the most useful tools inside the realm of food preservation, sustainability, and shelf life. With that being said, I hope there is something new you have learned from the concept of sugar caking, whether it be about shelf life, moisture sorption isotherm, water activity, and moisture content, or even how to analyze data. Hope to see you in the next one.